Hello, Flat Earth researchers, debaters and debunkers. Let's do some Mathmagic today to see just how easy it is to bamboozle billions of people into ignoring reality and real physics and instead putting their faith in mathematical models of a spinning globe Earth orbiting the Sun. So what we're going to look at today is converting distances into imaginary curve, and this is a really fundamental aspect of the whole thing that needs to be understood, and discernment needs to be used. It's especially difficult for anyone who is fluent in mathematics to actually do this, to take a step back and simply discern the difference between what is measured in reality and what is conceived in a mathematical model that has actually no basis in what has ever been measured. So no curvature has ever been measured on the Earth. The radius of the assumed globe Earth has never been measured. Of course, you can work out what the radius is supposed to be if you have some kind of circumference. And of course we have these citations of Eratosthenes and what have you, making measurements and predictions, and so they have interpreted that as us being on a globe with certain dimensions. But that's all just contrived through interpretation of these mathematical equations that are a mixture of real measurements and concepts and put together in a way that of course appears to make sense. And because of the predictive nature of mathematical models, this is why it's passed off as scientific fact, because of course in science, if you want to adhere to the scientific method, you are supposed to make a prediction and then test it, and if your predictions come true, then your theory would appear to be correct. But mathematics takes a mixture of real life measurements and imaginary elements, puts them together, and even though you can make predictions, it doesn't necessarily mean that that is a fact of our reality. It's just conceptual and appears to be a working model. So this is why we need to understand that converting distances, which are real life measurements, into imaginary curves is done through calculations. Alright? Big difference. So, of course, in the real world, using geometry, for example, is really useful, and other aspects of mathematics that, of course, are very useful. I've got a tin here, and there are all sorts of dimensions that we can measure practically, and we can also make predictions about certain other dimensions that we maybe didn't measure directly. You might want to work out the volume. You might want to work out what the circumference of this lid is. Of course, we can do that, for example, with a piece of string, and then measuring that piece of string and seeing how many centimeters or inches it is. That's one way. But of course, we can also take a ruler like this, and we just find the centimeters here, put it across, roughly across the middle, and we can measure a diameter, and we can do this a few times to get something a bit more accurate. And so it turns out this has got a diameter of 14 centimeters, and of course from that we can work out what the circumference will be, and it will work. It's very predictable and works fine in the real world. So we might have a situation like this, where here's our representation of a tin. Now of course it doesn't matter if it's the same size, this can be any scale, makes no difference. That's the beauty of this. It's just an illustration of the mathematical formula, and we've got a center point and we want to see what our radius is, or the circumference. Okay, well, we know that the circumference is 2 times pi times the radius, right? Or you can just do it as pi times the diameter. We have a diameter of 14, so equals pi times 14. Yeah? And And once you do that, pi times 14, I've done it already on a calculator, turns out to be 43.9, so let's just put that as 44. 44. The unit is centimeters. All right? Voila. Okay? No contest there. Works fine. Okay? We had a radius. We actually measured a diameter, and from that diameter we could work out the radius. Works okay in the real world. But when it comes to the globe Earth, no one actually measured a radius down into the center of the assumed Earth, did they? Didn't start with that. It started off with measuring distances on the Earth. So like this, we can take a measurement of this distance, or I can walk across the room and make a measurement, a physical measurement of my steps or strides, or take a ruler and do it, and there are many other methods we could measure distance for hundreds and thousands of miles. Okay? The thing is, the distance is just that, it's just the distance across the surface. Let me just take my tin for example, you can go across a level surface, like my arm, or you can go, if you want, around a curved surface. But the distance that you go doesn't translate into any kind of shape, it's just the distance that you travel. So it doesn't prove anything about the shape of the Earth when you have a distance. What we have, of course, that is measurable are maybe distances from a ground point, such as the North Pole, and then outward from there. We have where the sun is at its zenith. Okay, we can do that. We can make certain assumptions about distances between certain points on the Earth, but none of that dictates any rotundity of the Earth. As far as we experience, it's just a level plane, and going any distance across that doesn't change whether you represent that as a flat line or a curve. So we got our mathematics. It works for knowing a radius that we measured. We could have measured the circumference. So there are various ways we can verify this, and the formula works. It's based off measurements. Okay? But when it comes to the globe Earth, all right, this radius here of what is it supposed to be? Something like 6,000 km or something. I can't remember exactly. All right, that's never been measured, has it? No one's ever done this measurement. What we started with was just measurements of distance. Distance. Yeah. That's all. Distance on the Earth. All right. You can't measure the distance to the sun or the stars. None of that's been done. The only physical measurements ever made on the Earth are those of us traversing the Earth. And you can, of course, derive calculations for a model from shadows from sticks or down a well, if you want, if you're Eratosthenes. And of course, this particular story is seen as almost like the foundation of the globe Earth model. That Eratosthenes measured some shadows and passed them off as curvature. But the thing is, that doesn't tell you anything about the reality of the sun. It works fine on a level Earth with a local sun. It's just the way it is. You can interpret it any way you want. So Eratosthenes didn't determine the circumference of a globe Earth. Again, the word circumference can be used to describe a circle on a flat plane. So you have at least those dimensions that are measured or assumed from a certain place to another place, like the equator. Yeah, but that's just across land and sea, in which the shape or form of that land and sea is not dictated by those measurements. Yeah, so a big difference. The radius wasn't measured. Yeah, so it's nothing that you can confirm. You can only confirm it in a mathematical model once you have assumed certain distances. So let's have a look at how distances on a flat Earth would have been converted into this imaginary curve. It's really quite simple, and it just involves tweaking this kind of formula, and hence it's so easy, because it's so simple, to bamboozle people into believing in the mathematical model of a globe, because it looks so similar to a mathematical model of a biscuit tin. Alright, I've zoomed in on the whiteboard so you can see it more clearly, hopefully. Now, here is a top-down view of a body of water, or oceans, with land masses on a level Earth, okay? So we might be able to measure some distances here, but what we're going to do is just create some boundaries first in which we're going to create our map with. So let's just do this. We go here and here, alright, okay. So this land and sea within this box is all we're going to reveal in our map. All of this over here doesn't exist as far as the people looking at the map are concerned, okay? So we've got this bordered off area that's going to be converted into a map, or what is level sea and land turned into a curved ball Earth. So what would we do to start with? Well, we would be able to measure distances. Let's just say, let's just say this is the north here, and this is the south, and this is the west, and this is the east, whatever. And we can maybe traverse from here to here, like this, and we can measure that distance, just as we can walk across this floor, we can walk all the way across here, and we can actually measure that distance, right? And we could do the same going the other way. And we could keep on doing this across all this land and sea, all right? And eventually we'd end up with a grid like that. And then we can make up a coordinate system. We could have A, B, C, 1, 2, 3, and that can be along the sides, or you can start somewhere in the corner or in the center. It's entirely up to you. And once you have everyone agreeing on the same thing, then they can follow these coordinates and these headings of north, south, east and west and get to the place they need to get to, with the distances already measured and worked out for them. So that's all you need for navigation. You don't need to know how deep down the Earth goes or its full dimensions. As long as you have a certain area of a much larger place mapped out, people can then follow this map and stay within its boundaries, completely unaware of anything that's beyond it. So what we have is measured distance, all right? So let's just take that distance, and let's say, for example, it's 40,000 kilometers. This from here, point A to point B, is 40,000 kilometers. So of course we can do it like that. The distance, 40,000 kilometers. That's an illustration. Doesn't matter whether it's to scale or not, we're just illustrating that it's a distance measured across a level surface. Well, we can do a simple thing, is we can then just say, all right, I'm going to take that distance of 40,000 kilometers and I'm going to call it my circumference. And point A and point B, in my scenario, I'm just going to join them up. Point A is here, and point B is here. And now I have a circle. And I know the circumference is 40,000. That's the number I've given to it. Measured in reality, measured in our real world, the distance, okay? So we've got a circumference now, we've just called it that, based on the real world measurements we made across a level surface. But now we're going to call it a circumference. And what would I do then? I've got a circle, so I'm going to put that center point in the circle, and I'm going to imagine a radius there. I didn't measure the radius, I didn't measure any curvature, I just measured a distance, but I've turned it into the circumference of a circle for my model, and now I'm going to work out the radius. Yeah? Now we can do that with the same mathematics that we used before and arrive at a radius that we can say is a constant for our spherical Earth. Now what we've got here is one line, yeah, one line. And whenever you're doing, if you're illustrating aspects of navigation, you might assume that you're looking at a circle that is cutting through a globe. That's not the case. What it is you have one line turned into a circle. Okay, so you can call it, for example, the Great Circle route. So, you know, you could have just a, you might have traversed just a section here, all right? And that's just part of your imaginary circle, maybe from here to here, all right? So whatever distance that is, you could say, well, that's part of my circle here. And you're going to have degrees because you've already been able to calculate a radius, and then you can turn those degrees into distance. For example, 1 degree is 60 nautical miles. Yeah? Okay. So once you have assumed that your distance measured is a circumference, you can then do mathematics to arrive at a radius. Remember though, with the tin, wherever it is, where did I put it? With the tin, we really did measure the radius, okay? With the spherical Earth idea, we didn't measure the radius, we just calculated it based on a distance that was measured. And that distance doesn't dictate what shape the Earth is, but we can make it this circular shape and do some mathematics. Should we just go ahead and do the maths? We can use the same formula. Circumference equals 2 times pi times r. Okay, just put the multiplication signs in there. Okay, all right. But in this case, because we don't know what the radius is, we do know what the circumference is because we got our measured distance. Okay, so it's actually going to be 40,000 equals 2 times pi times r. Alright, we want to get rid of the 2 to start with, okay, so what we do is divide this by 2 and divide this by 2, which cancels it out basically. 40,000 divided by 2 leaves us with 20,000, okay, and we've got 20,000 equals pi times r. Now we want to get rid of the pi. And because we multiplied in the first place, but we're trying to get the answer to r rather than c, and we started with c, we just eliminate pi by dividing by pi here, and dividing by pi here, which will get rid of it, okay, and then you'll be left with r. Let's do it on the calculator, bear with me. Follow along if you like, get out the scientific calculator or whatever, okay. So we're going to basically take 20,000 divided by pi, which you can do on this, okay, and the answer is there, okay, 6,366, all right, so we worked out that r equals 6,000, what was it, 366 kilometers, all right. Didn't have to measure it, just worked it out. And of course, being able to do this, make this prediction, is what would make people believe that the mathematics is sound. But again, the measurement started with a level Earth. The only reason a curve is imagined is because we joined up points A and B to make a circle, and then we did this mathematics to work out what the radius should be if we assume that we're on a globe Earth, all right? Very, very different, okay? Measuring this and its diameter or radius or other aspects of it is absolutely fine and practical in the real world. When you say you've measured the Earth's curve, that's not true because no one ever measured the radius, which is what you needed to start with if you're going to measure the Earth like a cookie tin. All right, real maths versus fictional maths. Understand the difference, and welcome to Flat Earth. Thank you very much.